let's think more about shrinking the interval where we know the objective function is minimized along this cross-section, and can we reuse function evaluations so we don't have to evaluate the objective function more times than we have to. So let's say I had these alpha values and these y values. You would look at these and say, where is the minimum here? It's definitely between this one and that one, right? This might not be the actual minimum, but it might be between these two, it might be between these two. So we would say, okay, I'm going to use the rightmost side of this interval. I'm going to go from 0.3 to 1. So here I'm doing that, and here I'm going 1/3 of the way in from each side, or you could say 1/3 of the way and 2/3 of the way. So I have this setup of x points originally. I'm not graphing the y values here. And then when I shrink my interval toward the right, then I can reuse this function value, so that's great. And I can reuse this one, but these two I have to evaluate separately. I can't just reuse this one. And then you might say, well, 2/3 and 1/3 aren't magical numbers. Maybe I could try 1/4 in from each side, or 1/4 and 3/4. And so the same thing here, same decision that I want to shrink and use the right side of my interval rather than the left. And then I'd go from 1/4 to 1, and then here's the values you get going 1/4 of the way in from each side on that. And I'm getting closer to being able to reuse that one, but I still can't exactly reuse it. You might try 1/5 and 4/5, and again, you can almost reuse it, but not exactly. And so then there's maybe some mystery number where you can reuse it, and we need to figure that out. Here we're saying if you have to shrink to the right, we could also look at if the function values were like this, then you'd say, okay, the minimum is between those, and then we would shrink to the left, and it's the same thing. And again, hopefully this mystery number works. So let's think about that mystery number actually. Let's think about this length. So let's call this value here 0.6-ish. It's probably not 0.66666 because we already tried 1/3 and 2/3 and it didn't work. But let's call that value r. So we've got the length of the entire interval here is 1, and this length is r. And then, oh, I forgot to move this pointer arrow. Think about how long that is and how long that is, and try to set up some kind of relationship to say what's true about these arrows and those arrows to figure out what this value of r is. This length is 1, that length is 1. This length is 1, that length is r. This length is r. What's this length? It's 0.3-ish. We could say that this is r from 0 this way. So this point would be r from 0 that way, from 1, which leaves this as 1 minus r. So here's our length, and we could say maybe the ratio, sorry, a little bobble there. Maybe this ratio and that ratio are the same. So we could say the old part over the old whole, these two, is equal to the new part over the new whole value, those two, which is saying 1 over r over 1 equals 1 minus r over r. And that is a problem where you could pause the video and solve it. So go do that. And when you come back, we'll talk about it. Welcome back from pausing. So what do we get there? We get 0.618-ish, which is actually -1 plus the square root of 5 divided by 2. And that itself is a very special number. You might have heard of the golden mean, or the golden section, or the golden ratio, which is what you get by solving this polynomial. And that itself is 1 plus the square root of, positive 1 plus the square root of 5 over 2, or 1.618-ish. It's also called phi or phi. Here's a quick question. What is 1 over phi? Well, we can just do 1 over that. Oh, let's try that again. 1 over that. So that looks awful similar except without the 1, right? So if I just did equals 1 minus that, sorry, that minus 1. So the golden ratio minus 1 is equal to 1 over the golden ratio, which is a lot like what we were talking about here. So here's some fun with miles and kilometers. Does that look awful similar to that? So that's kilometers per mile, and then miles per kilometer is that, and awful similar to that. So that's actually an easy way to remember the conversion between miles and kilometers if you're in a country where miles are important, which is not most of the world. All right, so the big reveal here is this method of shrinking our interval, trying to keep the minimum between our endpoints, is called the golden section method. So maybe we should go way back up here and reveal that name now. And that's what was here too. This isn't the golden section, it's 1 over the golden section. All right, so the nice things about the golden section search are that each step we're very predictably shrinking the length of our region. So I could tell you in advance how many steps of golden section you need to get your length of your region reduced by like 90% or whatever. So it's very dependable. And even though we have kind of 4 points shown here, each time we shrink the interval, we can reuse this one, we can reuse the endpoints, and so I only have to evaluate the new value, the function value, once per step. So that's pretty nice. You might be thinking, could I do better? Could I shrink my interval, instead of putting these kind of far apart from each other, what if I put them right near the middle? And we'll think about that in the next video.